right, so here's where we were. We were talking about the gradient vector, and what we found is that the gradient vector points in the direction of fastest increase, which is, again, it's interesting for two reasons. For one thing, again, this is a very natural thing you want to talk about. Another thing, it's a geometric characteristic of something that we initially wrote down for algebraic reasons. Okay, so next theorem in that vein. Another reasonable question. Suppose that you go in the direction that we just agreed on. Namely, okay, I'm going to run in the direction of the gradient vector. How fast is the function changing as I move in that direction? Right. So, what is the value of this unit directional derivative? Keep in mind the unit directional derivative. This is what you multiply by distance to get a linear approximation of change, or you might say the unit directional derivative is the rate of change with respect to distance traveled. Right? Well, that's a pretty interesting thing to want to know as I'm running in this direction. I would like to know that every yard that I run, the function that I'm very interested in, how much does it change? So, perfectly reasonable question, and the answer also relates to the gradient. The magnitude of the gradient is that answer. It is that unit directional derivative. And this is a very easy calculation. We know that directional derivatives are computed with dot products with the gradient. Saw that just a few minutes ago. We just agreed that the best unit vector is the unit vector pointing in the direction of the gradient vector. Namely, it's the gradient divided by its own magnitude. That's how you find unit vectors in the direction of a given vector. And here, you notice we have a vector dot itself, which gives me a magnitude squared. And altogether, then, I have magnitude squared divided by magnitude, which is magnitude, right? So the rate of change with respect to distance, df ds, if you want to, some people like to write it like that. Rate of change with function with respect to distance in the optimal direction is the magnitude of the gradient vector. So I like to rewrite these two results as follows. Rather than asking two questions and having the answers both relate to the gradient, let's rewrite it as the two geometric features of the gradient vector. Go back to the very first day of class. What is a vector? A vector is a direction and a magnitude. We represent the magnitude of the length. So a direction and a length. The two geometric characteristics of this gradient vector are both natural. The direction is the direction of fastest increase. The magnitude, the length, your preference, is the rate of change in that direction. Rate of change with respect to distance, of course. We don't know how fast we can run. Pretty good? That's quite surprising. Again, we defined this gradient thing, we defined it algebraically, and it's super geometrically natural. Notice that in both of these calculations, it's because we have previous understanding of how the dot product works that allows us to draw these conclusions. Right? So as we predicted, having geometric understanding of this helps me get geometric understanding of this new thing. Okay. All right. Here's another neat geometric feature of gradient vectors. It has to do with level sets. Let me remind you what a level set is. If we have a function, some real valued function, a level set says we're going to look at a single output value. Let's say C, right? And the level set corresponding to that output value is the collection of all input values for which the value of f is C. So you might say, let me rewrite this a little bit. You might say f I'll just say f equals c on that curve. So this is a level set of our, some function f. Okay, so here's my claim. Here's my connect. What does gradient have to do with this picture? The claim is that the gradient vector at a given point, specifically a point on this level set, the gradient vector of that function is always perpendicular to the level set. Now again, that's very geometrically, it's a geometric statement, right? Because we're talking about perpendicularity. And again, it's surprising because we define the gradient algebraically. It's always weird when that happens. So if you're looking at a level set of a function, by the way, quick reminder, don't forget, level sets of a function live in the domain of the function, right? So they're not like graphs. Graphs live in this weird world that we created where we put input variables and output variables on the same axis. It's super strange. Level sets live in the domain. Gradient vectors, if you think about it, count up the number of different components you have in a gradient vector, you get one per each variable you're taking a derivative with respect to. You get one for each input variable. Gradient vectors also live in the domain. And at a given point, where there's a level set, where there's a gradient, those are always perpendicular. So it's pretty surprising that this is true. It is not hard to prove that this is true. I'm going to walk you through that argument. It's no big deal. So keep in mind, we've got a level set. So everywhere on this surface, everywhere on this surface, we have f is constant at this value c, this single value c. Everywhere on this whole surface. So, if I'm here on the surface, f is c. If I'm there on the surface, f is c. F is c here, f is c there. If I were to take some curve moving along the surface, the value of f everywhere along this curve, always c, because we're on the level set. We're not moving off of this level set. F just doesn't change. So here's the strategy. If I want to show that the gradient is perpendicular to this surface, I'm going to say, well, let's suppose we have some tangent vector to the surface. I'll do this in blue. Suppose I have some tangent vector. If, as I claim, this gradient is perpendicular to the surface, well, then the gradient would have to be perpendicular to that tangent vector. Okay. Let me say that a little bit differently. If I can show that the gradient is perpendicular to every tangent vector to the surface, well, then it's definitely perpendicular to the surface. So we've got some tangent vector given, and I'm just going to say let's use that tangent vector to construct a curve. Let's think about just some curve. It doesn't really matter which one. Some curve going through the level set strictly on that surface, on this level set surface, that passes through this point A, and whose velocity at that point is the tangent vector that you've given me, v. Right? Now I appeal to your geometric intuition. If you give me a tangent vector, that tangent vector is going to be the velocity of some curve. All right. Well, we're basically there, as it turns out. Couple observations. First observation is that this, here I'll do it like this. The value of f on this parametric curve is constant. And the reason I know it's constant is because we're on the level set, right? F is c. Everywhere on the level set, no matter where you're on the level set, f is c, constant. So if you move around some curve on that level set, f is still c. It's not changing at all. And that has a nice consequence. If this thing here is not changing, then it's pretty believable that its derivative is 0. Right? Okay. So now let's interpret what we've got here. What is this statement here saying? This says that, okay, well, this parametric curve, the point to this parametric curve is that it passes through at the point A with velocity equal to v. So what I have written down here is an expression representing how much is f changing if we're on this curve that's at A and moving with velocity v. Let me say that just ever so slightly differently. This says how fast is f changing when you are at A moving with velocity v. That's a directional derivative. Right? So when we say that this single variable derivative is 0, single variable derivative of this composition, we're really saying that the directional derivative of f at A moving with velocity v is 0. Which I have written down here. And don't forget, we can compute directional derivatives as dot product with the gradient. That means that I know that this dot product with the gradient is 0, and we all just get a knee-jerk reflex reaction. Dot product equals 0 means perpendicular, and we win. Right? So we've just showed, as required, we've just showed that the gradient is perpendicular to that tangent vector. Okay. All right. So a few quick examples. Okay, so first let's use the let's use the gradient to compute a directional derivative. Now we've already computed this directional derivative a couple of different ways. I think we did this the old-fashioned way, brute force, way back when. Then I think we used the Jacobian to compute this, or did we? Maybe we didn't. Anyway, we definitely did this the old-fashioned way back in 4.3. So let's use the gradient vector to compute this directional derivative. And the way we compute a directional derivative is with a dot product with the gradient. The gradient is just a matter of computing some partial derivatives. The gradient is the vector of all the partial derivatives with respect to one at a time all the input variables. So x partial, y partial, z partial. Plug in the point of interest, looking back at 4.3.1. This was the point we were interested in. A was 1, 2, 0. Plug that in. There's your gradient vector. Dot product that with your velocity vector. And there's that 10 that y'all may recall from when we did this example in 4.3. So it's now morally, is this any different from using the Jacobian matrix? Not really. The main difference, if we did this with a Jacobian matrix, is that instead of writing this funny little symbol, I'd write a J, right? And this would be a subscript. And then the other main difference is that this 202 column vector would be 202 row matrix, and it would be a matrix product instead of a vector dot product. But I mean, the arithmetic would be the same. All the numbers would be the same. It's just we're writing it down in a slightly different way. No big deal. Okay. Whoops. Here we go. Okay. Next example. Let's consider that same function. In what direction is this function increasing the fastest? These are usually very straightforward questions. If the question asks you, what's the direction of fastest increase? The answer is the gradient vector, right? That's the wonderful thing about it. So, we've already computed that gradient vector. That is pointing in the direction of fastest increase. And a terminological thing, when we say direction, typically represent that with a unit vector. So we've got to divide the above by its own magnitude to get a unit vector to represent that direction. So that's pretty straightforward. How are we doing? Is everybody okay? Okay. Last example is a little bit more interesting. Those were pretty pluggy-chuggy. But here's a weird one. Suppose we have this function here, and I want to consider the level set that passes through that point. Now, this is a function of 3 variables. So 3 input variables, real valued. A level set passing through this point is going to be a surface. A surface in the domain. The domain is R3. So we're thinking about this surface, and what the question asks us to do here is to let's find the equation of the tangent plane to that surface. All right. Here, this is a situation where the calculus of level sets is super convenient. If you were going to try to take a point of view of calculus of graphs, you'd be in pretty big trouble here. You could make it work, but it's so much easier to do this with the calculus of level sets. Specifically, let's look at this theorem here. This is a theorem about the calculus of level sets. Right? This is a connection between calculus of a function, derivative, certain kind of derivative of a function, namely the gradient vector, and level sets of that function. Namely, gradients are always perpendicular to level sets. So does everybody see what I mean by calculus of level sets here? This is specific to level sets. This theorem does not work for graphs of a function. This is only for level sets of that function. Okay, so looking at this question here, we're looking at a level set. Let's see, let me draw a little picture over here. Got a level set there. And at a given point that we are given, let's see, we're looking at that level set, at that point, and we are interested in the tangent plane to that level set at that point. And by the way, this is the level set where f is a constant. Okay? And let's think about this tangent plane. How are we going to figure out that what do you need to describe a tangent plane? You want the equation of a tangent plane? Well, you need a point in the plane. Cool, we're good. We already have a point in the plane. 1, 3, 2 is in the plane. But most importantly, what you need to describe the equation of a plane is a normal vector. I need to find some vector that I can call n, perpendicular to that plane. Good news, the gradient of f. That theorem that we just talked about, the calculus of level sets, the gradient of a function is always perpendicular to level sets of that function. And it happens to be the gradient is exactly the normal vector for this tangent plane that we're looking for. Is everybody on board? So, yeah, so let's punch up that gradient. The normal vector, I choose it to be the gradient. The gradient's computed by these partial derivatives. That's just, again, a little bit of calculus. On that given function, you can find those partials and plug in the point in question. There's your normal vector, your gradient, therefore your normal vector. And in the equation of a plane, don't forget, those then are the coefficients on the left side of the equation multiplied by x, y, z in the equation of the plane. And the last little deal, of course, is n dot x naught. You've got a dot product in with x naught to get the right side. Everybody happy? Questions? Okay. Alrighty. So, but yeah, make sure that you don't try to pull this trick if the question is to find a tangent plane to a graph. Or, likewise, if it asks you to compute the tangent plane to a parametric surface, right? If you have a parameterization, that's not the same as viewing it as a level set. It was a different story in that case. All right. Okay. All right. So that's 4.8. We're going to move on now to the chain rule. I want to remind you all of the single variable chain rule. I know you all remember the single variable chain rule. Let me rephrase that. I know you all are really good at applying the single variable chain rule in terms of if I were to give you some big symbolic expression that you know how to, outside in, however you want to call it, executing the chain rule. But let me remind you a different way to think about the chain rule. So importantly, the chain rule is about the derivative of a composition. Right? So specifically then, if you have two functions, let's say f takes inputs and gives outputs, let's call them x and y. And then, by the way, there's f then. And if you have g takes inputs and gives outputs, let's call them y and z, noting that if we're going to compose them, if what comes out of f is going to be what goes into g, we better think of g with y as its input because f spits out y's, and this is kind of a natural naming choice. Note G in the composition is written there. I remind you, be super careful about this. It's super common to get these backwards. You see, in the diagram, in our left to right way that we write diagrams, F is on the left, G is on the right. But when you write the composition, F is on the right, and G is on the left. And it's just about, you got to keep track of which one acts first. Writing a diagram left to right first means it's on the left, because we're moving to the right. The way we write functions, if I were to stick some value of x into this composition, right, unavoidably the one on the right really looks like the one that ought to act first. So we kind of have to write it like that. Okay, so it's a heads up, just be careful. Okay. All right, so let's ask about this composition then. The composition that, where we take x as the input and have z as our output, all together, what is the derivative of this composition? Now, I know you all have seen this before, and I just want to give you sort of a point of view on how to think about it, to set up an analogy with what we're going to do for the multivariable version that we'll get to momentarily. How do you use derivatives to take x, changes in x and infer changes in y? Well, we use the derivative of f. The derivative of f is a relationship between x's and y's. But let me say that a little bit more specifically. Multiplication by f prime. The derivative is the factor that you multiply to get from here to here, to get from x velocity to y velocity. All right, how do we get from y velocity to z velocity? Well, again, we multiply by a derivative. This time we multiply by the derivative of g. Said differently, the derivative of g is the factor that you apply in going from there to there. So altogether, if you give me an x velocity and you want to know altogether what is the corresponding z velocity, well, you've got to introduce as a multiplicative factor, you have to multiply by the derivative of f, and then a second factor is the derivative of g. When you multiply by something and then you multiply by something else, you multiply by the product of those two factors. Okay? So the idea then is the factor that you multiply by in the composition has to be the product of the factor that you multiply by here and the factor that you multiply by here. Factors multiply is the big idea there. Okay. All right, so with that set up, notice our result here. The derivative of f gets multiplied by the derivative of g. because it's the succession of multiplication by these two factors that accomplishes what the derivative of the composition actually does. So one way to read this is that the derivative of a composition is the product of the individual derivatives. Okay. Now, I do want to call your attention to one little detail before we make a multivariable version of this. Let's look at where are these functions evaluated? F prime is evaluated at A. Why A? Well, go to this picture. F is being evaluated at this point A. It's at that point A that we're interested in how changes in X translate into changes in Y. So the derivative, likewise, evaluated at that same point A. All right. Likewise, the composition is being evaluated at A. It is at A that I'm interested in knowing how X changes translate into Z changes. So the composition, we'll note in 2 seconds, is evaluated at A. Right? But seemingly, an eyebrow raiser, and some students are confused by why this would be. How come we don't evaluate G prime at A? G prime, what's the deal with it? It's got to be G prime of F of A. Why? Ultimately, it's very natural. Because we're evaluating G prime, I claim, at F of A. And you can see that right here on our diagram. G prime, like G, is evaluated at that point, which is F of A, because that's the point that comes out when you plug A into F. Right? I mean, so that's just kind of what it has to be. That's the only thing that really makes sense. In fact, if you were to write G prime of A, where's A? G prime has never heard of A. The only numbers that go into G, and therefore G prime, are numbers that are values of Y. Y is F of X. A is a value of X. So G prime of A wouldn't make any sense at all. G prime of F of A is natural. Okay. All right. So thus, the mysterious little F of A. That used to bug me when I was young. They never explained that to me, and of course, once I drew the picture, it makes sense. But anyway, okay. So let's do a multivariable version of this. It's highly, highly analogous. Here's the picture. Now, we have multivariable spaces here, but look, it's the same. Look, we've got a function here, F, that takes inputs and gives outputs. I'm calling the inputs x's. Okay, there's multiple x variables. There's x1, there's x2, whatever. There's multiple input variables. I'm going to call them all x of something. X vector, you might say. And it gives out y's, y1 and y2. Then I might want to compose. I might want to consider, what happens when I take those y outputs and put them into this function g. Takes in y's and spits out z's. Right? Well, in this scenario, I could very reasonably ask if the x's are moving with a certain velocity. Well, correspondingly, the y's are going to be moving with a certain velocity. And then, but if the y's are moving with a certain velocity, then correspondingly the z's are moving with a certain velocity. And what's the relationship between all these different velocities? And specifically, what do I do to any one of these vectors to infer the next vector? Okay, so we have a process for that now. There's a million different ways to say it. We can talk about directional derivatives, Jacobian matrices, right? What I'm going to do, give me 2 seconds. What I'm going to do here is I'm going to talk about this in the language of derivative transformations. Yeah, question?
For the velocities, does it matter if the number of input variables line up? Like, for example,
no.
R2 to R4, R4 to R7?
Doesn't make any difference other than it's harder to draw a picture of. But arguably, like if I wanted to go from R2 to R3 to R2, then I would just draw the third axis there, but it's a little harder to visualize. Yeah, I made it 2 to 2 to 2 out of laziness. Yeah, artistic laziness. Okay. So let's talk about how these velocity vectors are related by derivative transformations. And remember, ultimately that's what a derivative transformation does. A derivative transformation is the thing that by itself, on its own, computes directional derivatives, namely turns input velocities into output velocities. So what about f? Given f, how do I turn this x velocity into a y velocity? Well, it's by applying the derivative transformation of f, that df matrix, linear transformation. So df is what turns this vector into that vector. How do I turn y velocity into z velocity? Well, the derivative transformation here. So if I want to turn x velocity into y velocity and then finally into z velocity, what I'm going to do is I'm going to apply the derivative of f as a linear transformation, and then after that I will apply the derivative transformation of g. So let's write that down. Given that input velocity v, I apply the derivative of f, and then I apply the derivative of g. Whereas, on the other hand, a more direct way of getting, straight from there to there, given an x velocity, how do I directly relate to a z velocity? Well, the function that relates x's to z's is the composition. So the derivative transformation of that composition directly turns x velocity into z velocity. Right. So looking at this equation, given my starting x velocity vector v, I can either apply df, and when I'm done, apply dg, or I can apply the derivative of the composition. Either way, I get the same result. Both of these give me the velocity of the z vector. Another way to say that is that these two linear transformations are the same. This being as it is a composition is the same as that linear transformation there. And altogether then, what I have is that this rolls off the tongue really nicely. The derivative of a composition, the derivative transformation of a composition is the composition of the individual derivative transformations. So that's kind of nice, right? Again, rolls off the tongue very well. Now, don't forget that we represent linear transformations with matrices. Right, so I'd like to rewrite each one of these linear transformations as a Jacobian matrix. Further, don't forget that composition of transformations corresponds to products of matrices. That was our motivation for matrix multiplication in the first place, was that it should correspond to compositions. And so we recover a really nice result, computationally very handy. The Jacobian of a composition is a product of the individual Jacobians. And it's in strong analogy to the single variable chain rule. The single variable chain rule said the derivative of a composition is the product of the individual derivatives. It's really exactly what this says. This says the derivative of a composition is the product of the individual derivatives. Totally. Pause for questions. Okay. All right. In practice, we tend to use I tend to use this more because, again, for computational purposes, matrices are just more convenient than writing out a full linear transformation and all that's notation. So in practice, this is the one that we use the most. Arguably, this is the one that's a little more sort of fundamentally natural, I suppose. But in practice, this is what we're going to use. Okay. Again, importantly, notice that as the only thing that makes sense, G and its Jacobian are evaluated at f of a. Again, what else could it be? Right? Look at this picture. Here's G. G is being evaluated at f of a. A is way over here. If you were to say, let's evaluate the Jacobian of G at A, what is that? Where is that? I've never heard of that. At A. A is in a different world than f of A. Everybody on board? And per his question, in fact, they might not even be the same dimension. A might be a point in 2 space. F of A might be a point in 3 space. G of A might not even fit. That might be a square peg round hole situation. It doesn't make any sense. Okay, so let's see a quick example here. I'm not going to tell you what these functions are exactly. I want to have a streamlined first example here where we're not muddled by a bunch of, you also need to compute a bunch of partial derivatives, and I'm just going to give you exactly the bare minimum of what we need. We have a couple of functions that we're going to compose. Notice that f of 1, 2 is 3, 1, 0. Let's draw a little bit of a picture here. From R2 to R3 is what f does. And then G goes from R3 to R3. Like that. F of 1, 2, there's 1, 2, is 3, 1, 0. Okay, so there's kind of a little diagram of our setting here. Notice that I have been given the Jacobian matrix of f. That function at that point 1, 2, notice? At the point 1, 2. So I'm given the Jacobian of f, and then I'm also given the Jacobian of g. This Jacobian, now it's the Jacobian of g at that point, 3, 1, 0, which, recall, is f of a. Right? So we're given exactly the information that we need in order to compose. And the question finally gets around to asking is, oh man, I didn't mean to delete that. It's hard to delete just one thing but not the other. There we go. So the question says, suppose I'm then interested in the composition. Right? How would I compute the Jacobian matrix of that composition? And we'll get to the second part of the question in a moment. Is everybody on board for the first part of the question, though? Okay. Want to compute the Jacobian of the composition? Well, f is first, g is second. Careful. It's real easy to get this backwards. F, being first in that composition, is also first in the product, which means on the right, not on the left. So easy to get that backwards. Right? And then likewise, G, being second in the composition, is also second in the product, but second in the product means on the left. Got to be super careful about which way you go. Again, that's just how things, our notation, unavoidably, we kind of have to do this. Okay. All right. So that having been observed, we're just going to take these matrices and we're going to write them down and multiply them, just like the theorem says. Here it is. F's Jacobian is on the right. G's Jacobian is on the left. and multiply, good old, plain old matrix multiplication, crank it out, and there you go. Everybody on board so far? Okay. All right, now, you do have to be careful in this next part. Arguably, this question should have, there's some critical details that maybe should have been made more precise in the statement of this question. But the question says, where am I? Yeah, okay, I'll use black is fine. So we've got F from R2 to R3, G from R3 to R3. I didn't say what the names of the individual variables were, right? So implicit in how I wrote, what I was hoping would be inferred from how I wrote this is that x1, x2, and x3 are the variables in the R2, in the far left domain. And that, x1 and x2, sorry. There's only two input variables. And that G1, G2, and G3 are the variables in the eventual target space. Okay. So I'm going to just write that down, and if this were an exam question, you'd be very within your rights to say, hey, you didn't tell me exactly what you mean by G3, and I would owe you an explanation of precisely what is G3. I have to write something like this down. Okay, so that said, notice the second half of the question says, what's the value of the partial of G3 with respect to x1? So that's a specific one of the partial derivatives. That is a specific partial derivative inside of the Jacobian of the composition that we're interested in. And don't forget the structure of Jacobians, right? There's a very specific structure. Columns correspond to input variables, right? So this question is asking about a partial with respect to x1. That means we're looking in the first column of our Jacobian matrix. In that first column, there are the three partials with respect to x1 of the three output variables. We want the partial of G3. We want the partial of the third output variable. Therefore, we want the third entry in that first column. And looking at our product, third entry in the first column, boom. Everybody okay? Okay. All right. Never make as much progress as I want on a given day. But anyway, we're out of time, so we'll call it here for today and pick up here tomorrow. See y'all later. Have a good day.